Hi, Mick McQuaid here, welcoming you to the last video of day 5. That's the beginning of week 2. And in this video, we're simply going to concentrate on one exercise, exercise 3.7.8. And we're going to get a little bit ahead of ourselves because tomorrow we're going to be doing a lab in which we'll be introduced to a number of the techniques that we're going to use in this exercise. So it's just unavoidable that we're going to get a little bit ahead of ourselves, but not too much. And this should help with tomorrow too. So here's the exercise for today, exercise 3.7.8, and it's a simple linear regression of the auto data set and some variables that we've already seen the regression output from. So let's get started. So the first thing that I'm going to do is cut and paste this into my file, and I'm simply doing that as if I were going to turn it in. I'm not actually turning this in. This isn't a homework assignment to turn in, but I'm going to do this as if I'm turning it in. And it's on 2 separate pages, so I'm going to cut and paste it in 2 separate blobs here because otherwise I'll get the page number and the header and all that kind of stuff. And then I'm going to, let's see, I want to separate all of these. Okay, so this is separate. Okay, good. So I've separated all of these. Now I'm going to just put a comment character in front of everything. So there should be one comment character in front of everything, and then 2 comment characters in front of the things that I add that are not R. Okay, so I'm going to add the exercise number, exercise 3.7.8, my name in the form that I like to be called, McQuaid semester, and a blank line. Actually, I'll just leave that line blank. Okay, now anything that I do in R, I'm going to leave a blank line, and then I'm going to put in R stuff. And this is the auto data set, so I've got to load the auto data set. Now, we already downloaded the auto data set. If you recall, we Googled ISLR and auto.data, and the very second hit was the ISLR website, and one of the things on there was the auto data that we could pluck right out of there. And we could pluck it out in 2 different forms. There was the auto.data file, which I recommend against using, and the auto.csv file, which is what I downloaded and what I recommend using and what I'm about to use now. Then I put it into the correct directory. So I'm just going to assume that all that's been done. And so I'm just going to load it into R the same way that we did the other day. So I'm going to say read CSV auto.csv header equals T, and na.strings equals question mark. And then once I've read that in, I'm going to alter it. So I'm going to make a new copy of it, having said na.omit auto, and this will remove the 5 lines with missing values. And then I think I'll say attach auto, and then I'll say in-row auto to make sure that let me do it this way. This is in response to this. I want to make sure that I correctly omitted 5 rows, so this should give me 392 rows. And I'm going to attach auto, and the purpose of attaching auto is that I can work directly with the column headings rather than having to mention the name auto at every step of the way. Okay, so I'm just going to run these commands in R. And oops, I already have it. So here I'm going to just say rm list equals ls. Now I'm just going to do this again. Okay, so somehow I did not omit everything. when I said RM, I didn't get rid of everything. So here's what I'm going to do. I'm going to turn off R. Oops. What was I supposed to say? RQ? Okay. And I'll say RF again, and that'll turn R on again. And I'm just going to say LS. And I have cars and empty cars, which I don't necessarily want, but I don't care. Not a big deal. Okay, so I've got auto here. Now I want to use the LM function to perform a simple linear regression. So here we go. LM, simple linear regression with MPG as the response and horsepower as the predictor. Okay, so that's a simple linear regression. And notice that when I do that, I get very little output. What I've done, though, is created a linear model object. And so what I want to do is use the summary function to print out some more of the information that's in that object. Okay, and so I've printed out enough information now to answer these questions. I didn't save it in an object, so I created this object and displayed it. I didn't save it, though, which I'm going to have to do later. In fact, I may as well just do that right here. Let's just do this. I'm going to say LM MPG HP gets this. Okay, and then I'm going to say summary and then I just get this summary thing again. Okay, good. So now I want to comment on the output. And the first question is there a relationship between the predictor and the response? And I'm going to say in my, the way that I'm going to do this is have lines that, my answers are going to be on lines that have two hash marks or splats or whatever you call them, pound signs in front of them. And I'm going to say yes, as evidenced by the, by what? By the large T statistic associated with, now I could put in some LaTeX here. I could say with, oops, hat beta 1, or I could say also known as the estimate or coefficient for horsepower. And I'm just putting that in there for your edification. You don't have to put all that junk in there. You could just say yes is evidenced by the large T statistic associated with beta hat 1, or yes as evidenced by the large T statistic associated with the estimate for horsepower, which is this number right here. This is the estimate. This is the large T statistic. And we know that it's large because the p-value is so small. And I should point out that this is abbreviated scientific notation. So 2e to the minus 16 simply means that it's 2 and it's after a 0 and a decimal point, and 15, it actually is moved over 16 places, so it's moved over to past the decimal point and then 15 places more. So this is 0.1502. So it's a very exceptionally small number. And this is also a significance code. This is significance code that is the most significant of the possible results that are mentioned here. So I would say yes. How strong is the relationship? I'm going to say that it's relationship is fairly. In fact, let me just say the relationship. Relationship is fairly strong. The relationship is fairly strong, as evidenced by by the r squared equals 0.6. And then for your own edification here, I'm just going to note, here's the r squared, it's down here as 0.6, near the bottom. And for your own edification, I'm going to say that I would call this, so there are two issues here. One is simply the magnitude of the t statistic of the r squared, which is not really that high. Okay, I would like to see an r squared in the 90s rather than in the 60s. And the context, though, has to be considered. The other thing is the context of this. And the context is this is a well-studied issue. Gasoline combustion engines are manufactured by lots and lots of companies. They've been made for a century or more, and they're very, very well known. So explaining how they work shouldn't be rocket science. We should be able to get a pretty good r squared. If this were a case of a rare disease or some kind of brand new engine that has been completely untested, then an r squared of 0.6 might seem extremely strong. An r squared of 0.15 might seem extremely strong in the case of some rare disease of which there are only a few known cases in the world. But here we're dealing with something well known, and so I can call that fairly strong, but I certainly can't call it strong or very strong. And if it were less than 0.5, say, I would probably start thinking about calling it weak. If it were below 0.4, I would definitely call it weak. Okay, and I just tell you that just to give you some idea of where my thought processes are on this, and help you understand that experienced people, when they look at an r squared, don't just look at the numeral. It's just not just the r squared. We're also considering the context. Okay, is the relationship between the predictor and the response positive or negative? The relationship is, oops, sorry a second. This isn't that convenient, is it? The relationship, sorry about that. The relationship is negative, as evidenced by the minus sign in front of minus 0.157845, the estimate for horsepower. Okay. What is the predicted miles per gallon associated with a horsepower of 98? And I'm sorry to say I've cheated here. I already calculated this because it's tedious to do it. And I calculated it to be, let's see, so we take first the intercept beta naught, and that's 39.9, call it 39.9, I don't know, call it 39.94 plus 98, that's the number that we're asked, times minus 0.15, call it 0.16, and equals approx, and this is just, I remember it was about 25 miles per gallon, so it's something a little less than 25 miles per gallon, I think. Plot the response in the predictor. Use the AB line function to display the least squares regression line. Okay, so plotting is really easy. We just go plot, and let's plot the x first, so it'll be on the x-axis, and the y second. Oh, I didn't leave a blank line. Points off. Okay, and here's the picture. It's in another window here, so I'm going to have to grab it and resize it. And so there's the picture we get. And we looked at this picture before. When we looked at it in the textbook, it had more of a squarish aspect ratio, so it looked a little bit more like this, I think. put it over there, because now we're going to do the AB line. And AB line is a function that will add something to an existing plot. And what I would like to add is the line expressing, what did we call this? MPG HP, I think. Let's see if that works. Ah, that works. Okay. So that adds the least squares line from that model. So that's another, that model is an object that has a whole bunch of properties and has, among other things, a least squares line that can be accessed by this, by AB line. Let's see, use the plot function to produce diagnostic plots of the least squares regression fit. Comment on any problems that you see. And here I'm going to cheat again. I'm going to use some, I'm going to use this technique so we can automatically produce, you'll learn from the textbook that we can automatically produce 4 diagnostic plots at once, which is very convenient. And we can do it in the following way. This is going to create 4 diagnostic plots. Watch. Okay, and they're very tiny, so I'm going to expand them a little bit here. In fact, let me expand them so we can only see the first 2. So this first one is one that should look very familiar because we looked at this before when we were looking at residual plots, and we said that there was a pattern in there. So we're just going to say that again. The residuals show a pattern indicating we've left something out. And then we'll also talk about QQ plots. QQ plots tell us or compare the residuals to what we expect the residuals to be. And we expect the residuals to be normally distributed, and if they are, they will show up along this line here. And notice that they are systematically curved. We have a systematic curve in this direction, so no. QQ plot tells us. I'll just continue here. QQ plot tells us that the residuals are not normally distributed, which we expect them to be. And then finally, the other big thing, the scale location plot isn't something I'm going to go over anyway, but I do want to go over the leverage plot. So the leverage plot, unfortunately, here is really tiny. This is as big as I can get it and fit into this screen unless I move the screen around. It's just going to be too much. So what we see, so I'm going to tell you in a second that anything greater than 0.01 here is an indication of high leverage, and anything greater than 0.1 here is an indication. Anything, let's say, anything above well, in any event, so this dashed line, it says, is Cook's distance, and let me just tell you what Cook's distance is and what leverage says for this. So the leverage statistic can range between 1n and 1. So that's 1 over 392 and 1. We expect it on average to be p plus 1 over n, which in this case is about 0.05. And we expect Cook's distance for any point to be below 4 over n, or about 0.01. So we have about 20 points high leverage. And that's all I'm going to say about those points. It may not be enough to delete those points. We just know that these points have a lot of influence and we need to look at them. I would not say that they're influential enough. They're still, the highest one has a Cook's distance, the highest one has a leverage statistic of 0.03. That's still, to me, not that high. But we could delete those and rerun the regression and see what happens, see if we get a substantially significant difference. I doubt that we will, simply from looking at this data set for a while. It seems obvious that the thing to do is to add the quadratic term, which is what we did before. Okay, so that's it for this exercise, and that's it for today. And tomorrow we're going to continue with Chapter 3. We're going to do the lab. That's the main activity for tomorrow is going to be the lab. And we're also going to talk a little bit about a couple of other topics, or basically one other topic, but it's mainly about the lab tomorrow. So thank you for your attention today, and I look forward to welcoming you tomorrow.